So they had asked us that there was ClNO2 and it was reacting with NO, and equilibrium was established. This reaction was happening, and they had told us that there was. So they had told us the bonding of this molecule, and we had to draw the dot and cross diagram. Anyways, the reaction between ClNO2 and NO is first order with respect to each of the reactants. So you have a total of two reactants. So that's reactant one, that's reactant two, and it's first order with both of them. So it's that means that it's going to be Cl. NO2 concentration would be 1, and the other one is NO. Its concentration would also be 1. Okay, so it's first order with respect to each of the reactants, and there's going to be a K over here, which is going to be your rate constant. Now, after that, he then states deduce the units of the rate constant K when the concentration of both gases are measured in mole per dm cube and the rate is measured in mole per dm cube per second. So let's try and measure the unit for K. So rate is mole per dm cube per second. So I'm going to write that as x to the power minus 1. Okay, mole per dm cube, I'm taking it as x. Then you have K into the concentration of ClNO2, so that's mole per dm cube, and the other one is also mole per dm cube. Now, if I make K the subject of the equation, it's going to become K would become x minus 1 and s minus 1. Okay, if I simplify this, this x would get cancelled out. This x goes to the other side, it becomes x minus 1. Now I'm going to substitute mole per dm cube, so it's going to become mole minus 1 and dm would become 3. And S is minus 1. Okay. Is this clear, Sarah? Akib, is this clear?
Yes, sir.
So then the next one, state and explain whether or not the reaction could take place in a single step. State and explain whether or not the reaction could take place in a single step. So this is the reaction. And is it a single step reaction or not? What did I tell you about steps of the reaction? If you remember, what is zero order? Which step, if a reactant is zero order, which means it doesn't affect the rate of the reaction, which step is the reaction in? I mean, which zero order reactants, in which step do they belong? The fast or the slow step? ठीक है, चलो ठीक है, Akif, that's right. Sarah, is this clear?
Yes, sir.
So if any reactant is zero order, then it belongs to the fast step. And if a reactant is first order, then it obviously belongs to the slow step. Now, if you look at this equation over here, if the reaction, now listen very, very carefully. If one of them had been zero orders, let's say I remove NO and I replace it with 0. If NO's concentration was zero order, and which means rate wasn't dependent on that, then this would have been in the fast step and this would have been in the slow step. So that means there would have been two different steps. There would have been a fast step and there would have been a slow step. That means at least two steps are in the reaction. Do you get the point? Sarah, Akib, do you get the point?
Yes, sir.
Achha, on the other hand, if both of them are first order, like which is the case over here, if both of them are first order, then they can possibly be, it could possibly be a single step reaction. Like you could have ClNO2. I mean, the reaction is already given, so I'm just going to go to that. So look at this equation over here. It could possibly be a single step reaction because it's first order with respect to both. And that single step is the slow step. I mean, if there is a single step, then that means there's only one step that matters. That would be the rate determining step because there is no other step. So if you increase NO's concentration, the reaction would speed up. If you increase NO2, ClNO2 concentration, the reaction would still speed up. So with respect to both, the reaction would be first order. So my point is, multiple step reactions, although this is not necessary that it has to be first order with respect to both, but there is a possibility because they've highlighted the word could it happen? Yes, it can happen. You can get first order with respect to both if you just have a single step. Uh, so let me also check how this is answered. But you get my point. Akib, Sarah, did you get this answer, question?
Yes, sir.
Let me just, because they've given you 3 lines. Which year is the paper? One second. It's W19 QP41. So let me just. The W19 MS41. And this is what question? This is question number. This is the second question in the paper. Acha, where's the second question? Okay, seeing the number of moles, yes, and the number of moles of reactants in overall equation is the same as the order or in rate equation. Okay, that makes sense. So they're saying, I mean, yes is also yes. वो तो हमने we figured it out. The explanation is that total moles equal the overall order of the reaction. Okay, so remember I told you that if it's in the slow step, then this is one. I had also told you I had made a small point somewhere when we were doing this. Let me go over here. When we were dealing with mechanism. Okay, there was a small point that I stated at the end. It was probably this one. This one. I told you that the reactant coefficient, that is the coefficient is the moles, right? In the, like, this is 2, so that's the coefficient. That's the moles uh, in the equation. So the reactant coefficient in slow step is the order of the reaction. So if it's a single step reaction, like if this had been a single step reaction, the order for this would have been 2 and the order for this would have been 1. Uh, so order for this would be 2 and this would be 1. Whereas if it had been a multiple step reaction, so that means if it had been a single step reaction, then the total moles would have been equal to the order of the reaction. Like y would be raised to the power 2. Let me clarify this point in detail. Like if there was only one step in the reaction, okay, I'm assuming if there was only one step in the reaction, then x and this one step would have been the slow step because there is no other step, and y would be squared. So the overall order of the reaction would have been 3. That's exactly the same as the number of moles. But if you have multiple steps in the reaction, like if you have a step 1 and a step 2, then the overall order has nothing to do with the moles of the reaction. Do you get my point? Akib, is this clear? Sarah, is this clear?
Yes, sir.
Okay, like the overall order, I mean the same reaction, I've divided it into different steps. If there are multiple steps, then usually the moles that are involved in the reaction, I mean it's the same reaction happening over here. Okay, x first gets converted into these things, then it reacts with 2y to form z. So it's the same reaction, but I've divided it into steps. So then the order is usually not the same as the moles that are involved in the reaction. Okay, there are 3 moles of the reactants in the overall reaction, but over here the order is much higher than that. So that's, I mean, they're saying that's one indication that it could possibly be a first order reaction. Not a first order reaction, a single step reaction. But it was only for 1 mark. I said next one is an experiment is carried out in which the initial concentration of ClNO2 is 2 times 10 power minus 4. A large excess of NO is used. The initial rate of the reaction is 1 times 10 power minus 4 mole per dm cube per second. The rate of the reaction is due to be constant for the first 20 seconds. You're being asked to draw a line on the grid to show how the concentration varies for the first 0.2 seconds. So they have told us what is the initial concentration. I mean, there's ClNO2 over here. What's the initial concentration? That's 2 times 10 power minus 4. Okay, so that's correct. This is your initial concentration. And then he's saying that the rate is 1 times 10 power minus 4. It is a reactant. A reactant would decrease with time. I mean, the other axis is time. Okay, so the reactant would start to, it would start to decrease as soon as the reaction starts. And usually, initially, the reactant decreases very fast and then it slows down depending on the order of the reaction. Anyways, they have said that for the first 0.2 seconds, the initial rate is 1 times 10 power minus 4 seconds. I can use ratios that every second, like in 1 second, the concentration is decreasing by 1 times 10 power minus 4 mole per dm cube in 1 second, right? So in 1 second, this is happening. This is the gradient. Remember, rate is the gradient of the reaction. So I can simply use ratios that in 1 second, it decreases by 1 times 10 power minus 4 mole per decimeter cube. But they're saying that the rate remains constant for the first 0.2 seconds only. So I can use ratios. If in 1 second it's decreasing by this amount, in 0.2 seconds it should be decreasing by what amount? That would be x, and we can use ratios. So it would be 1 times 10. Let me do this. Yeah, कोई मुझे बता दे. It's going to be 1 e minus 4 into 0.2. ठीक है, 2 times 10 power minus 5, or we can say, let me just 1 second confirm this. ठीक है. So it's 2 times, नहीं, आखिर, I've made a mistake again in my calculation. ठीक है, it is 2 times 10 power minus 5. So that means that at the 0.2 second mark, this is the 0.2 second mark, the concentration should decrease by how much? It should decrease by 2 times 10 power minus 5. Mole per dm cube per second. Okay, so try and understand the two ways of doing this. Either you can sketch the gradient, or you can simply use ratios that the rate is given. That means that every second, 1 second, 1 times 10 power minus 4 mole per dm cube per decreases. This should not be second. So in 0.2 seconds, the decrease should have been 2 times 10 power minus 5. So my starting point is this. It's 2 into 10 power minus 4. This is my starting point. So if in 0.2 seconds it decreases by this much, so I'm going to subtract and find what would be the concentration. So it's going to be 2 e minus 4, e minus 5, the minus 4, and minus 2 e minus 5, and that gives me 0.00018, or we can say it's 1.8 times 10 power minus 4. So it's going to be 1.8. So this is hopefully 1.6. This is 1.7, and this would probably be 1.8. So this one. So it's going to be this one, and I'm going to draw a line. So in 0.2 seconds, this is what's happening. I says, did you get this, Akib? Sarah?
Yes, sir.
ठीक है, Akib, is this clear? Yes, Akib. I mean, this is, remember the rate. Okay, I mean, this part, people forget this part. Okay, the part over here that's mentioned over here. That they forget that, I mean, what is the rate showing? I mean, you have to understand what is rate. Rate is how it's the change that's happening. Okay, so they forget change with respect to time, right? And in this case, the reactant would be decreasing. So the value that you're getting in 0.2 seconds, it should change by 2 times 10 power minus 5. It doesn't mean that it's going to be 2 times 10 power minus 5. That if you're starting at 2 times 10 power minus 4, you have to subtract 2 times 10 power minus 5 because that would be the change. And then you're going to get the new value, which is 1.8. And actually, just hold on 1 second. So here, coming back to this, is this clear? Abu Rera, clear? Ali, is this clear?
Yes, sir.
अच्छा, next one, reduce the concentration of NO2 product at अच्छा वो उसने actually यहाँ पे पूछा, he's asking, no, he's saying the product now, reduce the concentration. So you have to be, again, try and answer this intelligently. Okay, the change that's happening, what is this change? I mean, this change over here. This means, I'm going to write it down, that 2 times 10 power minus 5 mole per dm cube of this thing over here, ClNO2, has decreased. Why is it decreasing? Because it has reacted. And react करके उससे क्या किया? It has made products. So ClNO2 product कौन सा बना रहा है? If you look at the equation, one reacts, it produces one. So in this case, if you go back, इतना ClO2 गायब हो रहा है. But this is the change that's happening. It's decreasing by this amount. So the amount of NO2 produced would be exactly the same. It would be 2 times 10 power minus 5. क्योंकि उसी ने जाके फिर आगे जाके it would have made products, right? ठीक है, अबू रैरा, अली, आकिब, Sara, is this clear?
Yes, sir.
Yes, sir.
अच्छा, then after 20 seconds, the concentration of ClNO2 remains constant. Explain this observation. Why does it remain constant? After the first 20 seconds. You have to read the question again. Okay, the initial concentration of ClNO2 is 2 times 10 power minus 4, and a large excess of NO is being used. Okay, there's a large excess of NO being used. So go back. NO, you're not running out of NO. So why does ClNO2 concentration stop decreasing? Well, let's say इसके you have 20 moles and you have 1000 moles of ये large excess में उसने कहा है ना. So the reaction is not going to stop until, I mean, it shouldn't stop until ClNO2 goes to 0. मतलब ये end में बचा रहेगा, constant हो जाएगा, because all of it can't react. You've added it in excess. So can anyone tell me why the concentration of ClNO2 after a certain time stops decreasing? मतलब reaction complete क्यों नहीं होता? Why doesn't it go to completion? Okay, 20, मतलब let's say 20, first molecule reacted, second reacted, third reacted, you had 20 molecules. 18 पे जाके let's say it stops. Why does it stop? Why doesn't it go to completion? वैसे ही guess करो, common sense का ये उन्होंने वैसे ही trick question पूछा हुआ है. And it is first order. First order का मतलब है कि वो reaction slow हो जाएगा, but it would eventually, it should go to 0. But the reactants can't finish, remember? This is what I'm explaining. He's added NO in excess.
So,
Yes. So, Akib, you're not running out of reactants. मतलब वो इसकी बात कर रहा है. This was what he was plotting, right? So there's always NO there to react with it. क्योंकि he's added this in excess. किसी और को पता है? टाइप कर लो अगर. If you... Sara, any idea? Burera, कोई idea?
No, sir.
Okay, this thing should, I mean, theoretically, technically, this should go to 0. मतलब completely react करना चाहिए. There's no reason for it to not react. Exactly, Ali, it's a reversible reaction. मतलब भी मैंने कहा था it's a reversible reaction. It's a trick question, ठीक है? कि reversible का उसने sign दिया हुआ है. तो after a certain time, what would happen is कि पहले तो वो forward जाता रहेगा, then these two would start reacting, and the reaction, a reversible equilibrium would be established, ठीक है? So it was just a trick question. Explain this observation. It's a reversible reaction and reaches equilibrium. Okay, the reaction would still be going on. They can, at the same time, the reactants would be getting produced again. So it's reversible. And reaches equilibrium. Okay. Just 1 second. Give me 1 second. Explain what is meant by the following term: half-life of a reaction. Okay. Remember this. It's a time taken for the concentration of a reactant to decrease by half. The right concentration of a reactant to decrease by half. You should write the whole thing. The other thing, rate determining step. It is the slow step in the reaction mechanism. It's a slow step in the reaction mechanism. अगले पे आ जाओ. अच्छा, now we're going to learn something new. क्योंकि इस question के लिए we would have to actually study a bit more. ठीक है? And this is related to experiments and P5. Okay, in P5, what do you do? So we studied pretty much P4 key. We studied most of the things except for this P5, this experimental related thing. Now we're going to study the minor details that would be involved when we are actually doing an experiment. So what are the things that could be involved when you're doing an experiment? Okay, so remember, it's all about laboratory limitations. But doing experiment is not that difficult. Okay? It's understanding how to use the apparatus and how to dilute a solution. How do you change concentration? So finding order of a reaction. So let's say I have a reaction. I have A and B reacting and they're producing C. Okay? This is what's happening. And somebody is asking me what is the order with respect to A. Okay, what's the power? What's the order with respect to A? Okay, Aage, what's your question? Nee, why are you saying zero order? Nee, if the coefficient is 1, then it's going to be first order. But the coefficient becomes the power, right? If there's a single step reaction. The problem is, I don't even know what the mechanism is. Akib, do you get my point? Okay, I'm not saying it's a single step reaction. I have no idea what the mechanism of the reaction is. Okay, is this clear? Yes or no? You can type in the chat. Whatever you're doing, okay, you can. Okay. So right now we don't know the mechanism. We don't know whether it's a 3-step reaction, whether it's a 10-step reaction, whether it's a 1-step reaction. Okay, so I have no idea what the order is. So I'm going to perform an experiment. And the first type of experiment that I'm going to do is, it's pretty simple. What I need to do is, I just need to change concentration. Change concentration of A and see how the rate changes. Okay, figure out what happens to the rate of the reaction. Actually, I'm just going to get rid of this. Akib, can you remove that? So, I said what I'm going to do is I'm actually going to take an actual reaction. Okay, let's say I have sodium carbonate reacting with two HCl's, and it's producing what is it, NaCl plus H2O plus CO2. Right? So I have this reaction that's happening, and I want to figure out how is HCl, what's the order of HCl, right? Now, the first problem that I'm going to have is that I can try and change HCl's concentration. And I can try and figure out the rate of the reaction. Okay? I mean, this is what I'm going to do. And I'm going to try and keep sodium carbonate's concentration constant. Okay? So it's a simple step that needs to be done in the lab. You change HCl's concentration. Make sure this is the thing that you need to be careful of, because you're not investigating sodium carbonate. Make sure all other variables are constant. And when you talk about variables, especially those variables that are going to affect the rate of the reaction. So all other variables apart from HCl's concentration, because that's the one that you're trying to, that's the variable, that's the one that you're trying to investigate. So make sure all other variables are constant. So what could be the other variables? Now, number one thing is, like, you do several experiments, the temperature has to be kept a constant. Temperatures need to be kept constant. Pressure needs to be kept constant, because carbon dioxide gas is being produced, its volume can be affected by pressure. What other things? Like if there's a solid, which I don't think is present in this case, the surface area of the solid or the type of solid. If you're using powdered, then use powdered. If you're using a solid piece of chunks, the chunk should have exactly the same surface area. And other reactant concentrations, they must also be kept constant. They must be kept constant. So what are you going to do? What you're going to do is, and the other part is, how would you measure rate? Because the thing is that if you try to measure rate, as I told you, rate was changing in concentration with respect to time. But changing concentration, it's very hard to measure. Like if you do this reaction finishes in 20 seconds. So how can you measure the concentration every single second? I mean, that's kind of impossible. So practically, what you do is you measure any change with respect to time. Okay, so in this case, and the other thing that you could do is you could keep the change fixed. So it would be actually 1 over time. I mean, the example that I'm going to try and give you is, like there's a 100-meter race and there are 10 runners running. So no one is measuring their speed. Okay, if there's a 100-meter race and no one is there trying to calculate with what speed is one runner running in meters per second. They don't have calculators. What they simply do is they have a fixed starting point and a fixed ending point. So the change is fixed. Let's say there's a 100-meter race. So the change is fixed. And there's a person sitting over here, and the only thing he does is he measures the time. Okay, and this is exactly what we are going to do. Because we're not interested in measuring the speed. We just want to know what is the relationship, whether the speed increases or whether the speed decreases, what happens if you change HCl's concentration. So we're not actually interested in even measuring the rate of the reaction. Okay? If we were interested in measuring the rate of the reaction, we would have done all the calculations. Okay? And the same is with the runners. Like if there are 10 runners running, you can clearly, you have a fixed mark, you set up a fixed mark, and they start at the same time, and you wait over here and you measure the time, only the time, because the change is fixed. And from that you can get an idea that, like, if one runner is running the same distance in 10 seconds and the other one is running in 5 seconds, that means the 5-second runner is twice as fast as the 10-second runner. So by just measuring time, you can actually you don't have to do all the calculations. You don't have to measure mole per dm cube per second. You just need to get an idea who's fast, who's slow, who's twice as fast, who's twice as slow. So just keep change fixed. So you have to find a mark in this reaction. You have to set up a mark. Like every reaction, you're going to change the HCl's concentration. So what is that mark that this reaction has to reach? So that mark, you can find that out. There could be several marks. I mean, I need to settle this mark. कि stopwatch कब तक measure करनी है, उसका time कब तक measure करना है. So there could be, in this reaction, there could be several marks. For example, one of them could be, let's say, who makes 10 cm cube of carbon dioxide the first. I mean, you're going to do several reactions. You're going to keep on changing HCl's concentration. You can figure out the rate, the effect on the rate of the reaction. So every time you have a 10 cm cube mark, you do the first reaction, you do the second reaction, you do the third reaction. You just take a stopwatch and see if the first reaction, the concentration is large and the reaction is fast. So it just takes 5 seconds for the reaction to produce 10 cm cube. The second reaction, you reduce the HCl concentration and now it takes 20 seconds to reach the 10 cm cube mark. So you just have to set up this mark. The other mark that you could set up is loss of 5 grams. You can, because carbon dioxide is being produced. So that could be another mark. ठीक है? Is this point clear? Sara, is this clear? Akib, Abu Rera, clear hai? Ali?
Yes, sir.
Yes, sir.
Achha, so remember this. No need to actually measure the rate. ठीक है? When you're trying to find the order of the reaction. Achha, the other thing, how would you change HCl's concentration? Because in your lab, let's say you're given a 0.2 mole per dm cube. I mean, no one gives you multiple HCl solutions with different concentrations. So given a 0.2 mole per dm cube solution, now you have one solution of HCl, marked HCl. You have to make several solutions out of it with various concentrations. So what you do is, you have HCl and you have water. The first one is HCl's concentration is, the volume of HCl that you're going to take is, let's say, 100 cm cube for the first experiment. And you're not going to add any water. So that means the HCl concentration is 0.2 mole per dm cube. In the second experiment, that's the first experiment. In the second experiment, what you're going to do is, you reduce the amount of HCl, but at the same time, you add 20 cm cube of water. So now you have slowly started gradually diluting the solution of HCl because you started adding water. In the third experiment, you can reduce HCl's concentration to 50 cm cube and add 50 cm cube of water. Then you can reduce it further, 30 cm cube, and you can add 70 cm cube of water. And the fifth point would be that you can have, let's say, 15 cm cube of HCl, and you added 85 cm cube of water. Now, the point of adding water is you have to keep the volume constant. Because remember, there are other reactants involved as well. Because if you change volume, concentration is dependent on volume. Concentration is moles over volume. So you can't touch the volume of the other reactants, like the other reactant in your solution, because you're not investigating it. The other reactant is, I mean, what was the other reactant? I think it was sodium carbonate. So you have to keep that fixed. Let's say you're taking 50 cm cube. Every time you're taking 50 cm cube. So the moles are constant. Every time you're using the same amount of sodium carbonate. So the total volume of the solution should not change when you're diluting it. Okay, the total volume at all cost has to be kept constant so that the other reactants, their concentration is not affected. Of solution should remain constant. And the last column would be, how do you measure rate? Rate would be 1 over time. You start the reaction and you measure time. 1 over time is going to be rate. Rate is inversely proportional to time. If it takes longer, that means it's slower. So every time you have a predetermined set mark, you start the reaction. Let's say 10 cm of carbon dioxide. The first reaction, mix HCl and water and sodium carbonate, and you wait. The first one would probably be the fastest because it's going to be more concentrated. And now it's getting dilute. And the ratio in which it's going to be diluted is going to be the same ratio in which the volume is decreasing. Like if it's a 0.2 mole per dm cube solution, so this is 100% the same concentration. So your concentration calculation would be kind of easy. If it's 80 cm cube, that means 80% is now HCl and 20 cm cube is water. So the concentration would drop by to 80% of this. It would become 0.16 mole per dm cube. So I'm just going to write the concentration next to it. The first one is 0.2 mole per dm cube because you're not adding any water. The second one, you're going from 100 to 80. So that's a decrease of 20%. So your new concentration would be 0.16 mole per dm cube. Okay, that's HCl's concentration now. The next one, you've reduced the amount of HCl to 50%. So your concentration also drops by 50%. It's now 0.1 mole per dm cube. And similarly, you can actually figure out without actually going into any moles calculation. The purpose of this dilution by adding water is that the concentration would start to proportionally decrease. 30 cm cube, that means it's only going to be 30%, so it's going to be 0.6 mole per dm cube. Okay, is this clear to everyone?
Yes.
Akib Ali, is this clear? Abu Rera?
Yes, sir.
चलो ठीक है, we'll continue with this in the next class. अभी ये खत्म नहीं हुआ, there are other methods as well. So we'll continue this in the next class then. Okay, take care. Allah Hafiz.